In this video, we're going to be looking a little bit more at chemical bonds and what causes a chemical bond and why they form. So from the other activity that we did on atomic interactions, you would have seen that there are different kinds of interactions that we actually saw, right? So here we have an example of neon-neon interacting, and over here we have two oxygen atoms interacting. And what we see is that those potential energy well diagrams are a little bit different. In this first case, between two neon, we had a relatively shallow well, and that didn't actually form any sort of new species. However, when we had the two oxygen atoms interacting, those actually formed a very stable new species, and that is actually a chemical bond. And so we really want to try to understand that in just a little bit more depth. One of the things to recognize is that interaction between the two oxygen atoms is actually much, much stronger, right? It's a much deeper well. And so what you saw is that we actually got a new species that stayed and formed and was stable and remained. And that's because the depth of that well is so great that this becomes, and things that are in lower energy tend to be more stable. However, between the two neons, yeah, there is a little bit of stability there, but it doesn't take much to actually disrupt those. And so we see that there are some differences that exist there. So why these differences in strength? That's probably something we're wondering. Well, all attractive forces, when we're talking about particles between atoms, molecules, ions, etc., they're actually the result of electrostatic attractions. And so we've got pluses and minuses that are attracting, and we think about sort of Coulomb's law in terms of how that plays out. In the case of neon, we actually have London dispersion forces that are being formed. We'll talk more about those a little bit later in a couple of days, I think. But in the case of oxygen, we actually have covalent bonds that are formed. And those have similar causes, that we have attraction between the nuclei and electrons of other atoms, right? So we've got the plus to minus interaction. But obviously the strength of those vary quite significantly. And really the reason that comes up is that it has to do with how the electrons are actually arranged in the new species. Are they really localized near the existing nuclei, or are we a little bit further apart? And that's going to depend a bit on some of the things that we previously talked about, which is, do we have space in orbitals for those electrons to get relatively close to the nuclei? So when we think about a chemical bond, you probably know some things about this already. A chemical bond is really a force that holds atoms or ions together, and that's what creates compounds. And it turns out that there are actually different types of bonds, but that all of them involve valence electrons. And so we'll look at those just a little bit more to try to understand some of the different kinds of bonding that exist. Most of the time when we think about a bond, we tend to think about covalent bonding. That's essentially a sharing of electrons. And that occurs between two or more nonmetal atoms, right? And so here we have our two little hydrogens coming together, and those electrons, we know that they're kind of bouncing around, they're in random spots, but they'll come together and they'll essentially share electrons, and we often represent that with a line to sort of indicate that there's a bond. And in these covalent bonds, the electrons are really being shared simultaneously with two nuclei, but it's actually probably more like a bit of a tug of war. So if we think about what's happening here, we've got our electrons, those are going to be attracted to both of the two nuclei at once, right? So they're going to be attracted to one and to the other, and so they're actually going to move around. And so if we look at sort of a distribution of what this might look like over time, what we'd see is something like this, right? More often those electrons tend to be between the two nuclei, but sometimes they're going to be over near one atom or near the other atom. And sometimes they're outside of it. So again, this would sort of be that distribution. So this gives us a sense of what that chemical bond actually looks like. So we can take that back and we can then think about that energy well diagram here. And so if we consider that energy well diagram, what we see is that initially, these two nuclei are relatively far apart, but as they come together, the attraction between the electrons and the nuclei will actually bring that to a little bit lower energy. That's going to make it a little bit more stable. That's what brings it down. However, if we push these things together even closer, then the energy starts going up because those nuclei start to get closer together, and that's what you saw in the pre-class activity. So what that means is that if we actually want these to find that right balancing point between the attractive and the repulsive forces, we're going to get to this lowest energy point. And that lowest energy point is what we call that bond length. And so that 0.74 is the bond length for this particular pair of atoms to be attracted to each other. And that has a certain energy level as well, which is, in this case, negative 436 kilojoules per mole. And so finding that balance between where we have the most attractive forces without having too much repulsive forces, that's where we actually get the most stable bond. And so in a chemical bond such as H2, where we have two equivalent hydrogens, it seems quite clear that, well, those electrons are going to be shared equally. But we might start thinking about two different atoms being involved, right? Because we know that bonds would form between hydrogen and chlorine, for example, so we could consider HCl. And we might start to wonder, okay, so if you're an electron in this particular bond, where would you want to spend your time? Would you want to be closer to the hydrogen, as would be represented by the red electrons here? Would you be split evenly and spend your time equally between the hydrogen and the chlorine and be represented by those black ones? Or would you want to spend more time near the chlorine? So think about our periodic trends, think about the attractive forces that would be applying in this particular situation, and see which of those two locations you actually think might be better. Do you think it would be better to be near the hydrogen, near the chlorine, or do you think it would be relatively equal? So take a few moments, answer that on the Google Sheet, give your reasoning, and then we'll come back and we'll talk about it for just a moment. Okay, so hopefully you've had a chance to answer that on the Google form. So now let's see what we're thinking here. So there's actually really good reasons that you could be thinking about either the hydrogen or the chlorine, right? In the case of the hydrogen, we actually have a relatively small atom, so those electrons could get pretty close to that, and we know distance plays a big part in terms of the stability and that lower energy state. However, if we're thinking about chlorine, well, in the case of chlorine, we have a Z effective of 7 versus a Z effective of 1 if we're talking about hydrogen. And so that Z effective might actually be much more attractive. So if you go with either of those, that seems pretty good. And the black sort of says, I think these things are going to balance out. Probably unlikely, but certainly a possibility. It turns out in this case, well, the purple actually ends up being the better location. Again, chlorine is bigger, so the electrons are further away, but that higher Z effective turns out to be the more important one. Now, you could imagine this being relevant for lots and lots of different kinds of atoms. And this gets us to the idea of electronegativity, which is represented with chi. So electronegativity was developed by Linus Pauling, and it's really just a measure of the ability of an atom in a molecule to draw bonding electrons to itself. So for that H and that Cl, how good are each of those two atoms at pulling electrons towards themselves? And the difference in this thing called electronegativity between the two atoms in a bond gives us a sort of a measure of how equally shared or unequally shared those electrons are. And that gives us a sense of what we call the bond polarity. Or if those electrons spend more time at one end than the other, then that side of the bond would actually be partially minus. It would have a delta minus. So we often then are really interested in this question, which atoms would draw electrons in a bond towards them the most? So let's have you take a few moments, think about that, answer the questions on the Google Sheet, and again, think about our periodic trends. Think about what you know about size and attraction to electron, think about Coulomb's force, all that kind of stuff. So answer the next couple questions and then come back. Okay, hopefully you've had a chance to answer those questions on the Google form. Again, it's really good to be able to think about it on your own before hearing some of this stuff. And so electronegativity, when Linus Pauling came up with this, he actually recognized that fluorine was going to be the most attractive atom, right? And so looking at all the data, what you find is that fluorine is the most attractive for pulling electrons and bonds towards it, right? And that makes sense. It has a very high Z effective, right? 7 is typically the highest that we see of elements. And it's also one of the smaller atoms, right? Because we know as we go across the periodic table this way, right, our atomic radii goes down. And as that radii goes down, that means the electrons can get closer. And so he defined fluorine to have a value of 4. And then he developed all the other ones to be relative to it. So again, one was set to be 4, and then the others are all things. So this isn't directly something that we can measure, but it ends up being really useful. And the way that he then figured out the value for all these other ones was to look at molecules that had bonds and try to understand, well, in that bond, was it polar or not? Were the electrons more present on one end or not? And looking at how those things responded. And so what we see is we get this overall set here, and what you see is the electronegativity increases as we go to the right on the periodic table and as we go up. And again, that's because the atoms tend to get smaller and our Z effective tends to get larger. So again, going back to what we were thinking about with the periodic trends. Now this ends up becoming really useful and it is really helpful for us. And this will allow us to be able to understand more when we get into the properties of molecules. And so this becomes an important idea. So let's consider two different kinds of bonds. a carbon-nitrogen bond and an oxygen-hydrogen bond. And what I'm going to ask you to do is actually figure out, well, what's the difference in electronegativity between these two things? And in general, the less evenly that those electrons are shared, the more polar that a bond is going to be. So I then want you to figure out, out of these two bonds, which one do you anticipate would be more polar? So take a few moments, answer those on the Google Sheet, and then come back. Okay, so hopefully you had a chance to answer those. Okay, and this should hopefully not have been too hard. Really, you're just looking for the difference between these two. So the difference between carbon and nitrogen, we look and subtract those. We get 0.5 as opposed to a difference of 1.4 between that oxygen and the hydrogen. And so in this case, you would then use that to try to infer which of those two do you think is actually going to be more polar or more unequally shared. And when we think about bonding, this is kind of an important idea, that bonding is really a continuum. We can have some bonds that are really, those electrons are perfectly shared. If we took two hydrogen atoms as an example, right, those are going to be a perfectly non-polar bond, that those two electrons are equally shared, they're equally attracted to the two of those, and so there's no pluses or minuses that would end up there. However, if we have something where one of those two atoms is more electronegative, has a greater electronegativity, more of a pole of those electrons, as would be represented here, then we're going to end up with the electrons spending more time on the left side of this molecule, and that's going to create this delta minus, right? Because there's electrons there more frequently than there should be. Over on the other side, we're going to have a delta plus, right? The electrons spend a little bit less time there. And so this becomes a continuum. And just to try to make our lives a little bit easier, well, we sort of say, okay, let's throw in this kind of artificial line. Usually we say it's at 0.4, and anything that has a difference of 0.4 or below, we say that's pretty much evenly shared. And so we're going to call those nonpolar. And it's defined that way so that a carbon-hydrogen bond ends up being nonpolar. But above that, we actually have polar things. And so there's some range where we get to polar, but you can imagine at some point, right, the electronegativity is so different that that more electronegative atom essentially completely takes that electron away from the less electronegative atom. And that's what creates an ionic relationship, right? The electron gets transferred from one to the other. The point at which that happens, you'll see it in lots of different places. This figure has it at 2.0. At some point, you'll see it at like 1.5. So it just sort of depends where you are looking on what you find. So it's not necessarily quite as hard and fast rule. But generally what you tend to see is sort of if you have a non-metal, so something from the far right side of the periodic table, and a metal from the left side of the periodic table, that's probably going to form what we'd say an ionic bond. Again, have a large electronegativity difference where we just say, hey, that electron actually gets fully transferred. And then we end up with a full negative and a full positive charge. And so we kind of want to recognize that there are some differences there. Now let me show you just a little bit what this might actually look like and why we actually need to look at difference in electronegativity. So let's look at three different molecules here. Here we have LiH, hydrogen bonded to hydrogen, and fluorine bonded to hydrogen. And so these all have differences in electronegativity. In this case, the hydrogen is actually the one that's more electronegative. And so what we see is that the red in this diagram down here shows that high electron density. And so there's much higher electron density on that hydrogen. The lithium has a lower electronegativity, so has lower electron density and ends up being blue. If we have two hydrogen atoms, right, those are equally attractive, and so we end up with just a green all over. It's a nonpolar molecule. However, if we have fluorine attached to hydrogen, then we know that the fluorine is much more electronegative. It pulls the electrons to its side, leaving the hydrogen being less electron rich. And so we end up with that blue color over here. So this is where I just really want to highlight that it's not the atom that's involved, but again, it's that difference in electronegativity that's really important here. So we can then add this in essentially to our other periodic trends, right? We already talked about effective nuclear charge. We talked about atomic radii, ionization energy. We talked about electron affinity. Electronegativity really has that same pattern and same approach. However, this tends to be the one that we're going to use a lot more in class. Electron affinity is useful to kind of understand things, but electronegativity becomes really important because we talk so much more about bonds in class. So